Right, thank you, Paul, and thank you, John and Des, for a very insightful and indeed informative presentation, which is focused mainly on how to use reinforcing steel. What I want to talk about now is how we make reinforcing steel, and that's just to give a bit of understanding of the product, but mainly its properties to help you out when you're using reinforcing steel. Now, Pacific Steel, as Paul mentioned, we're the only manufacturers of reinforcing steel in New Zealand, and we use only scrap feed. So for New Zealand, the story for how ductile mesh and indeed reinforcing bar is manufactured starts with scrap, and it's all manner of scrap, nearly 300,000 tonnes a year and up to 90,000 flattened cars. But it won't be your old flattened car, because we generally only take steel from the top half of the North Island. And that's enough for our capacity, and the rest of the scrap is actually exported. Sims Pacific collect, sort and roughly grade the scrap into big piles, as you saw there. And when we're making a particular grade of steel, we've got a recipe, and we'll take a scoop from this pile and 2 scoops from that pile. We put it all together in our electric arc furnace for melting. Now, that arc furnace has 3 big electrodes, basically three giant arc welders. Now, when that's running, it'll draw the same amount of power as about 10% of Christchurch's peak demand today to run that arc furnace. All that energy going in there, what we wind up with is a 1600 degree very reactive brew, and we're able to react off the impurities in the steel, and they form a liquid slag on top, which you just see getting poured off the top of the furnace, and that actually gets cooled down. It'll get crushed and screened, and Winston Aggregates use it for roading aggregate. The steel, however, gets drained into a ladle, a 50-tonne ladle, and we take that up to another processing station. We do a little bit more refining, but this is where we add the alloys, the carbon, the manganese, and critically the vanadium, into the steel to make that particular cast what we're looking for. That ladle then goes up to the casting station. We pour the liquid steel continuously into 3 cooled, chilled moulds, and continuously pulling square billet out of the bottom of those moulds. And that square billet, 150 millimetres by 150 millimetres, comes out. It cools down. We cut it into lengths, which we call billets, and we store that ready for the next processing stage. So we store it by cast. Right throughout the steel making process, we're taking chemistry tests of that steel. Obviously, we take it in the ladle, well, in the furnace, we take it in the ladle, obviously, where we're adding the ingredients to make sure we get the steel within the right specification. And we also take a sample during the casting, middle of the casting stream. That sample we take during casting is attached to that 50-tonne batch of steel. That's the basic batch and unit of steel. And that cast result will stay with that 50 tonnes of steel right through our production process. So every bundle of bar or coil of rod that we make that will go into ductile mesh, the label will have that cast number on it, and it'll be linked to that cast result. And that's the same cast number you'll see on all of our test certificates. The billet that you saw being stacked in the billet yard, and again we stack it by grade and by cast number. We're going to hot roll that. We've got to heat it up. We put it in a reheat furnace. We heat it up to 1,000 to 1,100 degrees just to make it a little softer for processing. And you'll see shortly where it comes out of the furnace red hot, that billet, and it just goes through steps of going through 2 powered rolls, and it just gets squashed a little bit more in each stage. And we have 17 of these stands, so we can roll straight bar from 40 millimetre down to 12 millimetre coming off that mill. You'll just see shortly the billet coming out and into the furnace. You'll see here where it goes into the first stand, that bar's sort of going at a crawling pace. It's less than 1 kilometre an hour. But of course, as you reduce the section size, it gets elongated and has to speed up. And for instance, when you'll see it coming out, it's coming out as 25 millimetre bar, and it'll be coming out about 30 kilometres an hour at that end, and less than 1 kilometre an hour of the billet going in at the other end. In the bar, you'll see shortly where it comes out of the rolling process. It's red hot. It falls into grooves on a cooling bed and gets slowly air cooled. And that's what you can see there, the bar coming out. all nicely spaced, evenly air-cooled. And it's important if you just remember that picture. We'll come back to that shortly. Once it's cooled, we cut it to set lengths, and we've got a few standard lengths, and they're all given on that sizing chart that was on the seat when you came in. And we put it into roughly 2-tonne bundles. As we say, each one of those bundles has a label identifying the cast and, in fact, that specific bundle number. If you're going to make sizes smaller than that 12mm, one, it's coming out fast, but two, it's a bit too flimsy to make straight. So we can divert it up through another 10-module block, and we make coil out of that. And that's really what the feed for ductile mesh is made as. It's made as coil, and we go down to 5.56mm on that. I mentioned before about speed. When we're making a 6mm or 5.5mm bar, the billet will still be coming in at less than 1 kilometre an hour, but when it's coming out that coiler, the 6mm rod will be travelling over 300 kilometres an hour, just because of the reduction in section that it's gone through. So and the coil, if you notice, it came out red hot, and it's just got the same cooling as the bar. Comes out red hot, gets a slow air cool to give it the properties. So all seismic reinforcing in New Zealand is made the same way. It's microalloyed. So it can be hot rebent if needed and welded, because it gets its strength from the chemistry, not from heat treatment, as in the case of a quenched and tempered bar. Now, NZS 3109, the concrete structures standard, has a clause in there explaining, which gives a procedure for hot rebending if you need to do it. And when you follow that procedure, which really you'll see it duplicates that production process, it asks you to heat the bar up to quite a tight temperature range, so till it's red hot. You can rebend it and just give it that slow air cool. And what that's doing, because it's duplicating the production process, what you're going to do is, even though you've strained that bar bending it the first time, when you hot rebent it, you're going to return it to have exactly the same properties as that bar had when we made it originally. So you return all the ductility back to that bar, if you're following the procedure that is there in NZS 3109. If you didn't follow the procedure and you tried to do it in the rain, you would be making quenched and tempered bar. Where you saw the red hot bar coming out, when we're making quenched and tempered bar, we would be quenching that quickly with water as it came out of the roll. And it wouldn't be going onto that bed as red hot bar, it would be dark and black, because we would have taken all the heat out of the outside of that bar. And what that's doing is it forms a very hard shell in the circumference of that bar, which gives that bar all the extra strength, because you're starting with a steel that's basically a grade 300 MPa steel, but because you've quenched the outside to something like nearly over 700 MPa, the combination with you've still got grade 300 on the inside, the combination will give you a 500 MPa bar, and it'll give you 10% ductility, because it's got a lot of the ductility of the grade 300 inside. So a quenched and tempered bar will still meet the reinforcing standard, of course, with that yield and with that elongation, but it's getting its strength from the heat treatment. So, of course, that means you can't weld that, you can't hot rebend it, you can't galvanise that steel. And that's the difference between the quenched and tempered and the microalloyed. Now, fine, you don't generally plan on having to weld reinforcing or even hot rebend it, but things do go wrong on building sites, and when you've got a microalloyed bar, you can always rely on the fact that you can hot rebend, you can weld, and of course you can galvanise it. So how do you recognise that you've got microalloy bar? We like to mark our bar, so in the case of deformed bar, you'll see we'll write our brand Seismic on the reinforcing. We also have the strength grade. In the case of the one on the slide, it's grade 500, but we also make a grade 300 bar. And we put on the end, we note the method of manufacture being microalloy, just to make it clear when it's on site, you know what you can and can't do with it. And Pacific Steel used to manufacture a quenched and tempered bar in response to market demand, but what we were finding was there was a lot of confusion on site as to what could and couldn't be done with the quenched and tempered compared to microalloy, and we've just decided to take that decision, and we'll stick to the premium grade microalloy bar, and we no longer produce a quenched and tempered bar for New Zealand. So all Seismic bar now is microalloyed bar. Although we do put the Seismic branding on all our deformed bar, we also retain the the bar mark that's required in the New Zealand reinforcing standard, which in this case are the 2 horizontal bars and the missing deformation for grade 500, and grade 300 doesn't have the missing deformation. So it just has the 2 bars, and that's on the sizing chart that you have in front of you. Plain bar, of course, also needs to be marked, and you can see on the bottom there, that's grade 500E reinforcing bar. The reinforcing standard requires a bar mark of 1 dot and 1 dash, and that's traditionally how Pacific Steel has marked its bar. But from this month on, the bar, and certainly always the ductile mesh feed, has had the bar mark, as you see it there, 1 dot and 2 dashes. The second dash just being a mill mark to say that it's Pacific Steel. So all grade 500E plain in New Zealand should have a dot and a dash, and Pacific Steel grade 500E will have a dot and 2 dashes from this month on. But it's always been the same on ductile mesh. It's always had the dot and 2 dashes. Those markings on bar are about 700 to a metre apart, and on ductile mesh, being a much smaller diameter, they're about 300 millimetres apart. Now they get a bit hard to see on the mesh being small and can be flattened a bit during processing, and they're only on one side, but they are there, and they're on line wires and cross wires, so you can check for that bar mark on grade 500E steel. As I mentioned, the ductile mesh has the same mark as grade 500E bar. It has the same mark because it meets the same properties. It's 500 MPa and it's got the 10% ductility. Now, all the mesh manufacturers in New Zealand manufacture a true ductile mesh, and they all get it tested. They either test it themselves or get it externally tested. So they can provide test certificates, and do provide test certificates for their product. So it's more than just a ductile mesh, it's actually a structural mesh, because unlike the cold-drawn product that John referred to in his talk, this product is a true ductile mesh that Des mentioned and can be used structurally. And the thing to point out here is when you're, according to the standard testing reinforcing mesh, you have to have at least one cross weld in the test piece when you do the tensile testing. So that's just there to prove that the welding hasn't impacted on the properties of the reinforcing bar, which it never ever does. So you can rely on the fact that that mesh still has the same properties as premium grade 500E reinforcing bar, even with the cross welds in it. What should I look for in my mesh is a question we often get asked, and I think the most important thing is identification. It's important not just to have some steel on site and some test results. The important thing is to have confidence in knowing that the steel you've got is related to the test results that you've got. Now, I mentioned all the mesh manufacturers test their mesh, and they'll all apply a durable label to that bundle as they send it out with unique identification relating it to their tests. Now, most actual manufacturers in New Zealand now tag every sheet of ductile mesh because they know the bundles are going to get cut open on site. So even when you've laid out the full sheets of mesh, obviously if you cut it you'll lose it, but even the full sheets of mesh can be identified on site and related back to the test certificate. And a lot of the manufacturers actually send that test certificate without being asked for it, but certainly if you haven't got it, you can get it from the mesh manufacturers. So for me, that's the most important thing, being able to identify your mesh, being able to have confidence that the steel you've got and the test results that you've got are related. Another question we do get asked, though, is about the condition of mesh, and you can see here I've taken another clause from NZS 3109, the concrete structure standard. The first sentence, they explain all the variables that can cause problems on a mesh, but the important sentence is the second one that's been highlighted. Tightly adhering mill scale or surfaced rust do not have a detrimental effect. And we're talking about the concrete adhesion here. And in fact, most people will tell you a little bit of rust actually helps that concrete adhesion. I tried to show you in the photographs, these are just cold drawn and dented mesh actually, they're not a ductile mesh, but you can see on your left, when it's first manufactured, a cold draw mesh is very bright and clean, but probably when you see it, it's a bit more like the middle picture with a little bit of rust, and that's fine, as we say, probably helps concrete adhesion. But when you start to get to the stage where the rust's coming off in your hands and you drop it on the ground and there's flakes falling off, obviously you've got that friable layer on the outside, it's going to impact with your concrete adhesion, and you're probably better off sending that sheet back to us, and we'll put it back at the start of the process in our electric arc furnace, and getting a clean sheet of mesh. So just a quick note now, when you came in, you'll find on your seats a few seismic tools. One is the little thumb drive that looks like a bit of reinforcing steel, but also there is a what we call a bendometer, which we've put together with the Cement and Concrete Association of New Zealand, and a couple of things for that bendometer, where you can check the diameter of the bar and then the bend radius. The two things to remember are that this bend radius is for general reinforcing steel. Now, you're allowed slightly tighter bends on stirrups and ties, particularly with plain bar, but for general bending of reinforcing steel, that will give you the minimum bend radius. So because it's the minimum, it should fit on the inside of the bend as well, something to remember. And also there, the sizing chart, which I've mentioned in the presentation. You'll see it'll give all the standard bar lengths and sizes that we make, but it also shows all the bar marking. If we just start at the top, is the grade 300 plane. Now, traditionally, Pacific Steel hadn't been marking grade 300 plane, but from March on, you'll start to see it being marked as here with 2 dots. The reinforcing standard requires 1 dot for grade 300E, but we're putting 2 dots on. Once again, 1 dot for the bar mark, 1 dot for the Pacific Steel mill mark. So Pacific Steel 300E, 2 dots. Underneath that, the grade 300 deformed. As I say, it's got Seismic 300E, and it's also got the bar mark of the 2 horizontal bars joining two ribs, but it doesn't have the missing ribs, which means it's 300. Look down further with the 2 missing ribs is grade 500E. And the dot and 2 dashes on 500E plane. The bottom bar is a reed bar. So we manufacture the threaded reed bar with exactly the same process and from exactly the same steel as grade 500E. The standard does require that it has a bar mark, so every 800 mils or so it'll have 1 short rib, but yeah, it's really just to say that we do manufacture it and it's the same process, so it's a grade 500E seismic bar, although we can't obviously write seismic on the threaded bar. So yeah, happy to take those with you, and if you need any spares here, I'm sure we've got a few there. And if you've got any other ideas for other little seismic tools that are handy on site, yeah, let us know. But yeah, with that, I'll hand you back, Paul.